Calculus section 4.1, and we're going to look at arc length. Circumference for a circle formula is radius times 2 pi, or 2 pi times radius, and since multiplication is commutative, we could do it in either order. And this is actually a specific example of the general formula for arc length, where the arc length is equal to the radius times theta, where theta is the central angle measured in radians. Let's look at this example. So we have an arc that has a central angle of 150 degrees. The radius is equal to 3 inches. And what we're interested in finding out is how long is this? So we're going to use our formula, S equals R times theta. The arc length is what we're trying to find. The radius is 3. But then for theta, we don't plug in 150 degrees. Instead, we're going to convert 150 degrees into radians. So we'll multiply that by pi over 180. And if we simplify this, we can divide the denominator by 30, divide the numerator by 30, and cancel out the degrees as well. So we get that that central angle measured in radians is 5 pi over 6. So now when we multiply those together, we would get an exact answer of 5 pi over 2 inches. And to go to the calculator, we could multiply all that together and get about 7.84 inches. So that would be the length of this arc with that given central angle and that radius. Next example, we have an arc length of 50, a radius of 10. We want to know what is that central angle measurement if we calculate it into degrees. So S equals R theta. 50 is equal to our radius of 10 times theta. Divide both sides by 10 and we get theta equals 5. So that's not 5 degrees, that's 5 radians. So we're going to convert that into degrees, take 5 times 180 over pi, and that is about 286.5 degrees then. All right, next two problems. We can break down degrees into smaller units called minutes and seconds. If you think about a clock, you have hours, minutes, and seconds, and it's similar to that. 60 minutes is equal to 1 degree, so every degree that we look at on a protractor, for example, could be split up even further, and every minute is broken up into 60 seconds. So we want to know how big is this angle of 50 degrees, 20 minutes, and 15 seconds. One way we could do it is to get everything converted into degrees and then add. So 50 degrees plus 20/60ths of a degree plus 15. Well, if there's 60 minutes or 60 seconds in a minute, 60 minutes in a degree, we would take 60 times 60. This is 3,600. There's 3,600 seconds in just 1 degree. So now if we add all these up, we get that to come out to 50.3375 degrees. So there is that as a decimal. On your calculator, you can use some functions that are on there. For example, if you go to angle, and you find that by doing second angle, and there's a degree symbol on there that you could choose. There's also a minute symbol, and then to get the seconds, you would have to use the alpha and the quotation marks that's on the calculator, right above the plus sign. The other next one we have is 60.4 degrees. We want to convert this into degrees, minutes, and seconds. So one way to do it would be to rewrite this 0.4 as a fraction. That would be 4/10. And then I want to know 4/10 is equal to how many out of 60? I want to know how many minutes are in the 4/10 fraction. So if we solve that, we would get 24. So this is 60 degrees, 24 minutes. 4/10 of 60 would give us 24. The other option we have is if you type in 60.4, go back to the angle menu, and you scroll down, there's an option that has convert to degrees, minutes, seconds. So we could do 60.4 and this. It would also give you the 60 degrees, 24 minutes. All right, next, looking at linear and angular speed. First question, which feels faster? Spinning around on a 3-foot rope every 2 seconds. So if you think about that, if you're holding on to the end of that rope versus the Earth's rotation. There's 2 ways that we're going to look at this. One is actually the linear speed. So for this one, the distance traveled is radius times theta. So the length that we're traveling is the radius of 3. Because we're going around a complete revolution, that's going to be 2 pi. So if we solve this, we get an arc length or a distance of 6 pi. Speed is always going to be distance divided by time. This is our linear speed. So we're going to take 6 pi divided by 2 seconds. That's 6 pi feet divided by 2 seconds. And we get that you're traveling 9.4 feet per second. Compare that to the Earth's rotation. One thing we need to know about the Earth is that it has a rather large radius compared to the other example. We're going to say it's 3,963.2 miles approximately. And so for this one, we're trying to figure out the distance traveled. We would say the arc length is equal to that radius. And one complete revolution around the Earth is also going to be 2 pi. And if you multiply those, we get approximately 24,901.52 miles, traveling all the way around the Earth when it spins. And we want to figure out, for comparison's sake, what is the speed that you're traveling on the surface of the Earth as the Earth is spinning. So we're traveling 24,901.52 miles in 24 hours, spinning every 24 hours. And now we want to convert this into feet per second. There are 5,280 feet in 1 mile. So I'm multiplying by 1 essentially, since those are equivalent to each other. And the miles will cancel each other out then. And also, instead of hours, I want seconds. I know there's 1 hour equivalent to 3,600 seconds. And like we had before, hours and hours can cancel each other out. Multiply across in your numerator, multiply across in your denominator, and the speed that we are traveling just by standing on the Earth with its rotation is about 1,521.76 feet per second. And again, that is our linear speed. So clearly, the Earth's rotation is faster than this spinning rope. Here's our formula for that. The thing is that we don't really feel the rotation of the Earth. This one, for the rope, feels a lot faster. You can feel it pulling on you. And that is why we're going to look at this from another scenario. And that's called angular speed. What is your angular displacement divided by the time? So W is equal to 2 pi divided by 2 seconds. If we divide that, we get about 3.14 radians per second. Or in other words, that's 180 degrees every second. Every second you're spinning around by 180 degrees, or 3.14 pi radians per second. And in the other case, you're also spinning through a complete circle, 2 pi, in 24 hours. If I convert 24 hours into seconds, that's 86,400 seconds in a day. Divide those, and we get approximately 0.00007 radians per second. And that's why when you're thinking about the rope scenario, it feels like you're moving a lot faster. It's because you actually are spinning through the angle a lot quicker than you are in the case with the Earth. Example. So we're on a merry-go-round. It has a radius of 6 feet, and it rotates 5 times in 18 seconds. We're going to look for the linear velocity and the angular velocity. So for the linear velocity, it's going to be arc length divided by time. And for our arc length in this case, we have a radius of 6 feet. And we're going around 5 times. So we're taking 5 times 2 pi. If 1 revolution is 2 pi, then 5 revolutions is 5 times 2 pi. And that's happening in 18 seconds. Go to the calculator, multiply out our numerator, multiply out our denominator, and we're traveling 10.47 feet every second. So as you're spinning around, the distance that you're traveling every second is approximately 10.47 feet. The other question asks for the angular velocity. How many radians are you spinning through? Or it's easier for us to maybe think in this one in terms of degrees. But for this one, it's angular displacement divided by time. In other words, what is the total angle that you're rotating through? That'd be the 5 times 2 pi, or 10 pi. And you're doing that in 18 seconds. So So now if we calculate all this up, you're getting about 1.75 radians per second. Now if you wanted to take that 1.75 and convert it into degrees, you can multiply it by our conversion of 180 over pi. And another way to think about this is you're rotating through an angle of about 100.27 degrees every second.